I'm going to illustrate the use of the power rule as well as the sum or difference or constant multiple rules. So before I dive into these four examples here, I'm going to quickly summarize the rules that we'll be using to compute these derivatives. So first, the derivative of x raised to a power n is n times x to the n minus 1. That's the power rule. Then the sum, the sum rule states that the derivative of a sum of functions, so a derivative of f of x plus g of x, is the sum of the derivatives. You'll see all of these examples of these functions have several terms. So we can compute the derivatives of these terms and then add or subtract results afterwards. So similarly for the differences, the difference rule states that the derivative of a difference of functions is just the difference of their derivatives. So the derivative of f minus g is the derivative of f minus the derivative of g. And finally, we have, this was used throughout my last video, the constant multiple rule states that the derivative of a function times a constant is just that same constant times the derivative of that function. So if you have a function that say it's multiplied by 2, then its derivative is also multiplied by 2. So all these rules are going to be used in combination on these four functions here. So what we can do is take a derivative of 5x squared, add it to the derivative of 3.5, and then subtract the derivative of 9x to the fourth. So using the constant multiple rule, we have 5 times the derivative of x squared, which is computed using the power rule. So for the x squared, we bring down the exponent 2, and then we have x raised to the first power, because in the power rule we subtract 1 from the exponent. And then for the next term, we have 3.5, but that is a constant. So the derivative of a constant function is 0. And finally, we have minus the derivative of 9x to the fourth. So that would be 9 times the derivative of x to the fourth using the power rule. So that would be 4x cubed. And now all we have to do is simplify. So x to the first is the same thing as x. So we would have 10x. And then minus 9 times 4 is 36 x cubed. So that is the final answer for that one. Now we can do the same thing with the next example. We happen to have fractional exponents, but the procedure is exactly the same. So f prime of x would be minus 4, and then we have, by the power rule, 7/3 x to the 7/3 minus 1. And then moving on to the next term, it's just a constant function 3. The derivative of that is 0. And then for the next term, we have 5 times the derivative of x to the 5/3. And that plays out in similar ways to the first term. So we have 5/3 x to the 5/3 minus 1. So now we just need to go ahead and simplify. So minus 4 times 7/3, that's minus 28/3. The recording got interrupted, so picking up where I left off. simplifying this derivative, so we have minus 28 thirds x to the 7 thirds minus 1. Well, 7 thirds minus 1 is the same as 7 thirds minus 3 thirds, which is 4 thirds. So using a common denominator, we can carry out that subtraction. And then skipping over this term because it's 0 anyway, and we have 5 times 5 thirds, which is 25 thirds, x to the 5 thirds minus 1. Again, use a common denominator. 5 thirds minus 1 is 5 thirds minus 3 thirds, which is 2 thirds. If you're not seeing that, try writing it out yourself. I did write it out in the previous video, but it's something that needs to become second nature. That anytime you have, it's going to happen a lot, a over b minus 1 is the same as a over b minus b over b by a common denominator. So that's the same as a minus b over b. So you can see that in these examples, 7 over 3, so 7 is the a and 3 is the b. So we have 7 minus 3 over 3, and then 5 minus 3 over 3. So now we have a final answer for our second example. Now, for these last two examples, before we can take the derivative, we need to express the function as a sum or difference of terms. We do not have that right now. For instance, this function here is actually a product of functions, and we need to express that as a sum or difference. This last function here is a quotient that has to be expressed as a sum or difference before we can use the sum and difference rules. So in this case, what we need to do is take this x to the 3/4 and distribute it through this expression in parentheses. So when we multiply x to the 3/4 times x to the 17/4, for example, we need to add the exponents. When you have like bases, you add the exponents. You don't multiply them. So distributing, we get minus 6 x to the 3/4 plus 17/4. They already have the common denominator. That's good. So now you can just add the numerators, and you get 20 over 4. But you might as well simplify that. 20 over 4 is 5. So we have x to the 5th. Moving on to the next term, minus 5x to the 3/4 plus 5/4. Again, you can just add them very straightforwardly. So it's 8/4, which is 2. So we have minus 5x squared. And finally, we have minus 7x to the 3/4. So now we have 3 separate terms here that we can differentiate, and then we can add or subtract those derivatives. So what we get is y prime, using the power rule as we did before, because this example is now just like the last two, we have minus 6 times the derivative of x to the 5th, which is 5x to the 4th. Then we have minus 5, derivative of x squared, which is 2x. And then we have minus 7 times the derivative of x to the 3/4. So that would be 3/4 x to the 3/4 minus 1. Well, it's 3/4 minus 4/4, so minus 1/4. And now we can simplify. So we have minus 30x to the 4th, minus 10x, minus 7 times 3/4 is 21 over 4, x to the minus 1/4. And that is the final answer. For our last example, we have a quotient. So we need to break this up into separate fractions. So 5x cubed, so we can break up the numerator. You can't do this with the denominator, only with the numerator. So 5x cubed over x squared minus 6x to the 4th over x squared. And now you can simplify each of these fractions. In fact, there won't be fractions anymore. So x cubed over x squared, you subtract the exponents. So you get 5x. And then for the other one, we have x to the 4th over x squared. You subtract the exponents again, and you get minus 6x squared. So now we have a difference of terms, a difference of functions, so you can take their derivatives and subtract those. So the recording got interrupted again, so let's see if I can finish this without any further interruptions. So now our function is in the correct form for using the sum, difference, and constant multiple rules. I get f prime of x is equal to 5. Now x is the same as x to the 1st, so I can write it as its derivative as 1 times x to the 0. Then I have minus 6 times the derivative of x squared, which is 2 times x to the 1st. Now all I need to do is simplify. Well, x to the 0 is 1, so I just get 5 minus 6 times 2 is 12, and x to the 1st is just x, so I'm left with 5 minus 12x. More like a 5. And here we have our final answer. So we can see how, using all 4 of these rules in combination, we can compute the derivatives of any functions like these that are sums or differences of terms, or even if they're not, perhaps they can be rewritten so that they have that form, and then we can easily take their derivatives.